might be 2.0 because they have like smart contract. For example, in this case, probably we should have numbered it as like 1.0, 2.0, 3.0, oh, 4.0, and we're 4.0. So it's just a matter of numbering. But Ethereum at its core still uses the Nakamoto consensus. So I think that's what we are different from it, because we're not using proof at all. Yeah.
Thank you. And 다음 질문입니다. Next question is, which features will be strengthened or complemented in Bitcoin 4.0?
Firstly, Korea is not Bitcoin, and so strengthen or weaken. So what we hope is, as for the payment part, we are very confident that we are not losing anything here because we are just trying to solve the problem. Like we're making the budae. We are not trying to make a bad soup taste better. So that way, we're not just adding ingredients to it. We're just remaking the whole meal. So that's what we are strengthening. Like, so then what parts could we like actually weaken? So far, I cannot think of any. If you have a good idea, please feel free to point out the problem. Or actually, there are challenges. For example, if you want to do smart contract, you still want a fully replicated linearized log. And of course, theoretically speaking, this linearized effort has to be more expensive than just keeping track of a DAG. I think in that sense, it's just like if we compare our snowman to our avalanche, both are inside of Alpha system, then probably snowman will have slower performance compared to avalanche. But I think in that sense, it is still much better than like previous generations. When it comes to scalability, it's like a self-comparison for sure. Yeah, if you only do payment transactions, then you can have very fast speed. This is because the DAG solution is faster than before. So hope this answers the question.
Okay. 다음 질문입니다. There are already many so-called blockchain 3.0 networks like Algorand. It seems like the question is not only a matter of technical advancement, but of adoption by developers, which is arguably harder. How does Aba랩s seek to solve this issue, maybe?
Oh, that's a great question. So we are all also well aware of this problem. So we know that there's a huge gap between the theory and the system, and another huge gap between the system and the final business part. So the way we try to first break through or build a bridge across these gaps is the first thing is very simple, like open source the code in the end and let everyone run the system. And that sounds like a very trivial, simple goal. Like, why would this speaker talk about this? But if you think about every single coin you previously know, are you able to download the code? Are you able to run it? Are you able to easily join the mainnet as you would in Ethereum? Probably not, right? If you really want to renovate the space, you first have to make sure your product is usable and it works out of the box, not just played by those very few investors or super nodes. And that's what we strive to achieve. And that's also called decentralization. And that's also, I think, the main reason that makes our Aba랩s very different from other crypto projects. Thank you.
Thank you very much. And next question is, in PBFT, when the number of the consensus group is increasing, the speed of the consensus is getting low. So how do you think you can resolve this issue?
Yeah, so I think that's a common question, because consensus is hard to improve. Why could we, magically solve the problem? As you may notice, we mentioned that we only sample the network by K. So we only ask a very small portion of the entire network. That means, unlike PBFT, which samples the entire network, like you just simply ask all nodes and hope for like 2f+1 responses. In our case, we're asking K and just audit the majority out of this K member. For example, if you have 2,000 nodes, probably you only have to ask 10. And you just, draw some partial conclusion based on this single sample. And of course, it is much weaker than asking the entire network, because what happens if you happen to sample some Byzantine nodes or other versary nodes, then bad thing could happen, right? So for each sample, we're actually relaxing the PBFT problem to have a probabilistic, small size sample. And that way, we're trading off 100% safety guarantee for much better, scalability and more potentials for further trade-offs. So what we are losing here by, not following the paradigms of the line of PBFT-like work is that we think people are comfortable with probabilistic safety guarantee. And that makes sense because, even if you're a billionaire, the next day you wake up or you walk outside of the street, you can still get hit by the car. No offense, but, still non-zero probability. And I don't think, having a much lower probability of safety failure sounds like a bad idea. I mean, if the failure probability is very low, lower than your hardware failure rate, then this thing doesn't matter. So we're making this kind of trade-off. Hope that makes sense to you as well.
Yeah, thank you very much. I believe it is helpful to understand. And next question is, according to the Gaussian protocol, when a certain amount of the network is under attack, isn't there any possibility for network to be altered?
You mean in our protocol or sorry, could you repeat the question?
According to the Gaussian protocol, a certain amount of network is under attack. Is there any possibility for network to be altered, to be changed, to be altered?
Oh, that's a good question. So that's why designing such kind of protocol sounds easy, but it's actually really hard. So first of all, you don't want to ask a fixated like 8 neighbors because you don't trust those, K neighbors. You don't trust those K neighbors. And what you want to do is each time you have to randomize the choice of the people you're asking about, and then each time you're choosing different K people. If you repeat the process for enough amount of time, then math will tell you that you have already high enough safety guarantee. And in the case when the network is partially attacked, which could cause, so-called network partition, I guess. If you happen to sample some of them from the attack part, then what you will get, either the attacker just refuse to respond to request, and then you just hand there, no safety violation. But if the attacker just, responds to you with the wrong answer, or, it just equivocates his response with arbitrary answer, then the question goes back to the first case I talked about. It's guarded by math. So either he refuses to communicate, in which, the system somehow gets stuck a little bit, but it can use timeouts. So you can always introduce some reasonable synchronicity assumption into the system. So to overcome this, for example, if this sample of K nodes don't get back to me in a short enough amount of time, then I can do another sample. Hope this answers the question.
Thank you very much. And next question is, does new protocol need more 2/3 of good nodes still? And when a total number of nodes is less than 2,000, how high TPS and latency was shown?
So I think this is 2 questions, right? The first question is, sorry, the first question.
Is the new protocol still need more 2/3 of good nodes?
Oh, I see. It depends. So I actually asked the same question like to our theory guy, like Kevin, and he said it depends. And that's a very interesting thing if you think about it. So of course, you can tolerate slightly more than 1/3 of the Byzantine node in your network, but at the cost of losing liveness. So if you take a look at the paper, the white paper, you'll understand what it means. So you're basically trading off between, safety and liveness when the absolute, amount of adversarials in your network is huge. And the second question again?
Yes, second question is,
Oh, I see. So 2,000 nodes and above, right? So I think I didn't do actually more than that because the tendency already tells us, this thing, the throughput doesn't degrade as much as you may think, but I can somehow speculate. So think about the protocol. You only ask K people, and K, if it is a fixed constant, because it has to be fixed. It's actually a security-related constant. It's very weakly affected by N. So it barely grows, even when N grows to like as large as 1 million. Then I think in that case, there shouldn't be much degradation in throughput, because everyone is just asking K people, regardless of the network size. And there's no extra load introduced if your system scales up.
thank you very much for sharing your knowledge. This was the last question, so thank you very much. You can return to your seats. 네, 좋은 말씀해주신 테드인 강사님께 다시 한번 큰 박수 부탁드립니다.